Then beyond that, if you are seeing right, whatever in the phones, they have to they have to put up some money for the fabrication to set up a plant. Like you have a clean room or whatever nanotechnology center right here. You know the cost involved in it. How much cost is involved in getting the equipment done and its maintenance and how it can go wrong. Right? Even for a small college and for a small like lab setup, if it costs that crores, imagine about few $billion industry, which requires extensive plants, right? Is also, it is a complete island. They have their fabrication. And India, they are now willing to set up their fabrication labs here, right? Fabs. So this is the news all over. So we understand how much cost it incurs. So changing from one technology now to other is not that easy. We want to go below 2 nanometer, right? And the cost factor involved in it is really, really high than the technical limitations it has. No, someone? Yes. Thank you. And you can go to slide number 4. So that's how the current industry works. Even we have a technical glitches to go beyond 2 nanometer, that quantum tunneling will occur technically. But rather than that, what stops us is the money involved in it. So there are groups and roadmap strategies involved in generating or thinking beyond CMOS. So what are the approaches it can be? So there is a term called spectronics, which you will be hearing it frequently when we are into magnetics and stuff, right? When you are hearing about it, that is going to be the next generation computing as well as the memories. Now you have seen about memories, right? And you know of the computing at the later stage. Here we will be talking about the computing. And in detail, when we break it down right from say top to bottom approach, there are 2 approaches: top to bottom and bottom to up. Did I say it right? Right, you are correcting me, right? You are active. Good. So please be actively involving throughout the session, right? Next slide. Please, next, please. This is the summary, whatever I gave you, right? This is not alone that stops with the technology features, but also with the foundry fabrication task. You can see how it jeopardizes the chip nanometer design. Yeah, next. So we are in a stage to think there are alternative paradigms to do that, and nanomagnetic computing, can it be an alternative paradigm? One such approach for this beyond CMOS. Morning we have seen about this neuromorphic computing, right? So can this nanomagnetic computing also be a other platform to give us an energy efficient computing, right? Now we want a mobile phone. We want to use it for more than 24 hours and we do not want to charge it again, right? That's what we expect, right? When you do a fast charging, it gets in 2 hours, but it gets depleted than what it is charged for if you do a heavy gaming. So all this comes under the term energy efficient circuitry. So when you want to do an energy efficient circuitry, there is also a term called on-chip clock interconnects, which traditionally we use copper, but here we will be proposing graphene for it, and we will be exploring how graphene plays a role there. And what is this on-chip interconnect? That is used for consuming power lines are there, right? Whatever is inside your chip. That's what we are going to terminology we name that on-chip clock interconnects. So traditionally copper is there, and here we will be talking about graphene. Graphene, right? It means that many of you might have heard Nobel Prize winning thing, huh? No? Yes? Yes, no? Yes? Yes? Okay. So next slide. You can go, sir. Yeah. Next slide. So what is rebooting your laptops or your systems? Right, you basically do a reboot every time, right? When it is you're facing a severe crisis and you want to start from the starting. That's called reboot, right? That's called reboot, right? So basically the same thing, rebooting computing, what it means. There is a problem with the computing and they are going to rethink and revision it from the scratch. That's called rebooting computing. Right? One new terminology. rebooting computing. It's the keyword IEEE has picked up as one of its task force group. They generally form this task force group whenever there is a need and demand where they wanted to see emerging technologies coming in. So that is now with this computer society. All the CS people here is talking about why I'm here. I'm doing CS. No, right? It's all interdisciplinary, multidisciplinary. This is under the IEEE computer society now. Rebooting computing. You understand the term rebooting computing, right? So we are going to think beyond that, whatever it is there already. So what categories are there? There are many categories. One such is this nanomagnetic logic, which has been boxed in the blue, right? Nanomagnetic logic. And we will be seeing how this nanomagnetic logic is evolved and what are the contributions state of that. So here we can see that under beyond CMOS, generally it comes three categories. One is this emerging architectures, other is emerging devices, the other is emerging materials. So all three comprises of a technology. It cannot stand alone, only we are developing materials, only I am developing architecture, only I am developing devices. It does not work. All these are interconnected. So when you are thinking of a holistic approach and the solution, you will have to start from all three of this. Right? That comes a full picture. You may not necessarily be doing all these things, but you will have a team doing all these things. There is something integration engineers available who can integrate team A with team B and team C. It's how generally you code, right? You do not code all 134 lines or 160 lines by yourself. There is blocks, right? Particular blocks. Block A is done by team A, block B is done by team B, and then finally integrate it using a GUI. And then we finally show it is a demo project. This is the call the full project, whatever it is. This is a team of members. Put this. Same thing. First, right, we will focus on the emerging materials. As I said, replacing copper with graphene for this on-chip interconnects, right? That I will be talking on the emerging materials. Going forward, the emerging architectures. As we understand, architectures plays a crucial role. Whatever you have in the chipset, right? Everything is an architecture, which is a black box at least for us. It's patented, whatever it is inside that. So we will be talking the emerging architectures for this rebooting computing and see how gradually it will lead to a device, which is a nanomagnetic logic device and which reboots computing. Now it makes sense when we connect all these dots. Yes? Thank you. So next slide. So now, here comes why we wanted to do computing with only nanomagnets. There are many ways, right? There are many ways, yes, I agree. Here I will be telling you why we want to compute with nanomagnets. This is also one of the ways. Morning you heard about neuromorphic computing, right? You may think blind. That is one technology, this is other technology. With whatever technology excites you, you can follow that and you can adapt it and you can fix the state of the art. That's okay. It is not that this is the best, that is the best. Everything is a technology node and we are trying to adapt it for the future. So why computing with nanomagnets is nanomagnets is have a spin direction, right? Up and down. Everybody know, right? It is differentiated with zeros and ones. All digital is 0 and 1. We are not talking about any analog. Let us forget about the analog part. But the real world is analog. But let us forget for the time being. Let us consider only the computation part digital, zeros and ones, right? Analog is whatever I am speaking, it's a raw data, it's analog. And when you split it up into a binarization form, zeros and ones, right? Any data can be represented. That is a digital form, and we will be focused only on the digital part as of now, not on the analog part. That is the front end and back end, which involves the complexity to understand it in a bigger picture. Just I'm telling you what it is. Okay, why computing with nanoanalysis? We are talking about the energy efficient circuit. Do you remember? Energy efficient circuit they have been studied, right? This nanomagnets has this energy minimization so that we can use it to drive, right? They do not use them, even when the power is off, right? Still your harvest, then you can put in the hibernate mode and off it. And still when you turn it on, it restores whatever state position you have turned it off, right? That's the non-volatile nature of the nanomagnets. Still, like we have been using that for only memories, and now we want to expand that for computing, right? Memories and computing together in a single form. The next step. Yes, sir. So when we talking about this on-chip blocking and copper wrapping nanomagnetic logic, can you ask me, do you have a chip fabricated with this real time integrated with your mobile or laptop? Is there any chip on this nanomagnetic logic yet on the market for purchase. Yes, no? Yes, no? No. Yeah, louder, no. Why was this technology not in the chip so far? As I said, right, on-chip clock dynamics. So far, we are only doing with the copper. And when it comes to nanomagnets, right, you cannot use copper. Why? Because we know that copper is a bulk material, and even when you break into the size of the nanomagnets, what we are talking about, quantum tunneling breaks it. And there are a lot of disadvantages associated to it. So obviously, when you want to power your chip up in a real-time market, integrated into your system, like a laptop or a mobile, it has to be function standalone. It's not your lab prototype. You can tap in your demo device, power it up, right? Or your PCB board to connect it with wires. It's all standalone. So there has to be a on-chip clocking circuit which wanted to replace copper. So can graphene form a key part in that? Is that possible? We know the parameters of this graphene, right? And even in the 2017 magnetism roadmap, this states that graphene can play an important role in logic and logic devices. We are not just assuming graphene will do, but rather there are technical literatures where people have studied and reported that it could be one of the possibilities that's correct case it is not. So next. Next. So it's a little back. So, yeah. One back. Yeah, fine. So we need to have this energy efficient circuit. Here I will briefly picture two things. One is this graphene-based computing devices where we fabricated this graphene nanopatterns and analyzed how to manage two generations of that with application of the cyclic characteristics. And other on the theoretical study on that, everybody knows that graphene is not magnetic. Graphene is not magnetic, right? Any other say? Graphene is not magnetic. Yes, graphene is not magnetic, but there are some groups reported magnetism in that, and we are also one among them who has reported that tunable magnetism in the graphene. That's the feature altogether. Let's not go much deep into it, but have an idea that there is a possibility to tune magnetism in graphene. That could be one thing we can explore if you are interested further on that line of aspect. So next, I'm out of the camera. All right. Yes. So what are the new postulates we have proposed, right? There are, for making this magnetism into graphene, right, we have two tunable parameters. As I said, tunable, there has to be one or two or three, but we have picked two for using a bound-type schematic. Everything is logical. There are no random numbers, right? As I said, graphene can replace copper. That's not random. Okay, we will do graphene. People have reported instances that graphene can be used in the roadmap and other things. Likewise, we use a bound-type schematic to get into the depth of that and combine field of electric field and temperature. We tune it and we get thermalism, antiparamagnetism. We know that ferro, antiferro. 0, 0 is ferro and 0 to 1 is antiferro. Simple as that. 0, 0 is ferro, 0 to 1 is antiferro. Okay? It's polarization. So to get into that, we can also find that this graphene plays an important role as a choice of material. We will see the fabrication procedures in detail. But yeah, as a first year student, try to grasp whatever you can. I will try to simplify it as simple as I can. So next. Yes. So are we doing this strictly to get graphene magnetism, everything? No, right? We want to finally have it in something. It is not proven yet, but this is our proposed model of using this as a graphene microprocessor. Graphene microprocessor. People are doing research, and still it's not in the market. It's a great scope of error where graphene microprocessor can be keeping to avoid this heating issue, thermal dissipation and heating issue, which your everyday phones, right? You have a Redmi phone, you can, that's the meme, you can use it to iron your shirts. It produces that much heat, right? Even with 15 minutes of gaming. So that's how we are trying to eliminate that. Huh? So just don't grab only whatever parts I'm telling, with like chicken biryani, with this ironing. Try to also understand and mimic the technical terms behind it. Huh? This is just for correlation. Don't quote me anywhere. Huh? Next slide. So here is a fabrication conceptual diagram which we have fabricated, and we will be having a. We know that currently we are doing in the silicon substrate. Although there are different substrates. We currently speak with a conventional silicon substrate, and there's an optic form of it that is silicon dioxide. And on top of that, we are going to have a graphene wire, and on top of that, we are going to place a nanomagnetic. Like it's a binary wire. You want to propagate data, right? 0, 1, 0, 1, 0, 1, and you give something, and then you get something. This is a wire. It's a wire of magnetic logic we are trying to get. So this is the diagram. The next step. Here we will be talking about this patterning this graphic and the two-step approach we have invented and followed for this application procedure and the electrical characterization and what are these applications. And we have also plotted this temperature affected with effect, which however for as that with first and second year will not make much sense, but yes, as part of a technical presentation, it has to be formally. I'll walk through it. So next. So yeah, this is a typical diagram, right? You can see.
Sir,
the first one is silicon dioxide graphene, and we are going through a fabrication procedure in a simple form. First, we are following the PMMA, that is spin coating. Yes. So here we are doing this. The step one is this PMMA ELN spin coating, which few of you would have been into this nano characterization labs and and we have this first EPA. Morning, Professor Surya was explaining about this lithography, right? Electron beam lithography. There are many different lithographies. Getting into technical parts, I could hear a lot of I won't bore you. Please bear with me for 2-3 slides so that it makes sense. We are presenting something on fabrication and calibration. Quickly, I will take you through some fantastic slides towards that. Please bear with me. So the next is this, we are having the step 3, which is ED spin coating, and step 4 we want to do a second EDL due to that mass whatever we are having, and finally see this gives you something, right? We are having some graphite strips, few nanometers, close to 3 nanometers, fabricated as IEEE bonding. It took nearly 1 year to get this example. But putting it in one slide in 2 minutes does not make any sense, right? I agree, but it's a 1 year long process to get to this point. When you have a thin strip without broken graphene line of 300 nanometers between this and its characterized. So it involves a lot of stuff. But please not. This is how it goes, but yes. So to make it little colorful, the same whatever you have seen previously, we are trying to elaborate it little bit on the side approach, right? First, the same similar thing, whatever we have seen there. And this is the development, and this is the final stage in the sun picture. And you can see how this gold patterns are deposited and what are the masks in it. So this is the continuation of that, and what we are seeing. That is the final picture, right? The same picture what we saw in the final flow diagram. So this is all through this process. And here is a summary, right? This how we have been doing different bits of graphene. We cannot say we are talking about nanometers, right? But we want to understand how it works with different nanometers, right? So we have been doing for different bits and trying to see what is the breaking point and what when that the graphene should break, so that we can use it for high temperature application in space applications. That was the key thing behind it, and we had a good breakdown voltage where it is width plays a major role along with this voltage, right? So that is the key thing. We identified that it could be potentially be used as a replacement of copper or on-chip carbon dynamics. Long way to go, but still yes, preliminary successful experience. So these are the process sequence. If any technical knowledge is interested in what is the photolithography and what are the steps we use, and photograph using the operator, and right is this 150 model for the lithography, and etching is the plasma with this for graphic plates etching. Okay, motor radius. Next slide I will be having all the motor rates. So these are the particular feature size of 3 nanometer and the scan angle whatever we use, and the feature size is of 500 nanometer, and yes, closely we have to obtain up to 300 nanometer. The next. What are the characterizations of the graphene? Whatever we are talking about, that is for the fabricated graphene nanostrips. But this is for the plain graphene, monolayer graphene. And what are these captives? Because as Professor Surya mentioned, right, the material has to be defect-free, error-free, right? It should not have any other invariants into it. So the first step is the first step. We have to analyze what is the graphene, and we need to compare it with the literature whether we are working on a correct material or not. So everybody in every department domain does that. Right? A similar process. The next step. Similarly, the sizes of the substrate and what are the features of the substrate. Not more into that, even if it will not get into your mind involved. The next step. So this is an image, right? Colorful, not colorful, black and white. Yes, but this is the same image taken at this IIT Bombay, and where we happen to see this is not graphene. In this minute graph, one line will be that graphene. So this is gold patch with electrical character. Makes sense, right? Next, sir. So I said, right, this is in detail zoomed image where we have to see the surface roughness and edge roughness, and we are not getting a break with that particular point to measure tiny characterizations. So next, all of them in how what nanometers will be. Next. So we have graphene now. Now we want to place nanomagnetic on top of it. We have not fabricated it. This is simulation. How does it work? We wanted to send the energize the nanomagnetic. If something is there, it has to be energized. Energy can either be created or destroyed, a basic rule. It has to be transferred from one form of energy to another. Same applies here. You cannot directly pitch in any graphene dot or the nano dot placed on top of the graphene to have its power. Right? It has to be underneath, and electricity has to drive the nanomagnet to settle it at some state where it can perform computation, zeros and ones. Right? Because metastability comes into the picture and thermal fluctuation scripts in. You want to avoid that, you want to have a graphene as a base material, and you want to energize the base. So next. So this is the comparison between the graphene and the copper, and it proves very much practical to have it on the research table to see how it, in the real time it replaces it. There's a long way to go, and standards are being developed, and soon it will be in the market. The next. This is another interesting thing from this magnetism and graphene. Like I said, few groups have reported other than ours. So this is one Bautai schematic from this group. They tend to use this graphene nanoflex itself for computation. What we are trying to do is use graphene as an energizing material and put dots on top of it and have a computation. But what they try to do is use graphene itself as a computation device. Having a Bautai scheme and zeros and ones, it's a majority logic, right? Most of you would know what is majority logic. 0, 0, 1 gives 0. Right or wrong? 0, 0, 1 gives 0. Majority logic. Right or wrong? What is majority logic? You have 3 gates, say 3 fingers. You have 3 apples. Out of which 2 are apples, 1 is orange. Now which wins? That's the majority. That's the majority logic you have everywhere. Right? Whatever is 2, 0, 0, 1. Output is 0. You have 0, 1, 1, output is 1. Makes sense, right? That's the majority logic. So that is the key thing for every whatever we are going to talk about this presentation. So these are the quick observations on the graphene part. We had it on a low complexity two-step application and cost-effective method to replace copper with graphene. We have been talking about these emerging materials and the heat for the gases. Now we are going to enter into the architecture perspective. Now we can connect the dots, whatever we are walking through the first 10 minutes of the presentation. So next. So this is as a brief background I have given why we want emerging architecture to be developed now. Okay, so now the stage is set. Now I will walk into few technical details of what this emerging architecture means for us. So next. This is what excites me. Yeah. In the graph. Yeah. All computer science graduate students will be honored now to hear this word. Even with materials and digitals, right? We use this terminology. As now we want to do all the spatial recognitions, even your mobiles, right? We're talking about all the real-time edge computing. So when you want to meet that demands, you want to have your architecture ready for that, right? So to meet that, what are the difficult challenges identified by this international roadmap of devices system? That's an international body where people from various countries and continents work together to frame a particular disability challenges and what are the envisaged results. They identified that they wanted to have a beyond CMOS architectures, which is also in line with this nanomaterial logic. So next slide. So this is a brief background on nanomaterial logic and what it is. We have been talking about all the spatial recognition and stuff in the CMOS, right? But everything has to be started from the start. As your president rightly said in the morning, the computer was this big and now it's in your fingers, right? In your hands. Similarly, everything has to start from the start, even from the nanomaterial logic, right? As I said for this majority logic, it has to start from that and go with this 1-bit adder, 1-bit subtractor, 1-bit multiplier, and come up with 64-bit addition, and then finally scale it up for this AI architectures or whatever we are talking. It started in 2000, and still the research is going on 2 decades now, and still no product on the market. The difficulty is in getting it to the market. There are many challenges which needs to be addressed. It's one key challenges which we addressed in the past few years is digital logic arithmetic. We have been trying to come up with a convolution architecture using this nanomaterial logic, and how does that can fit into any portable AI algorithms. That's a long question, and we are trying to go on the way, right? And we will also walk through in this presentation. So next slide. So this is the binary wire I'm talking about, right? You have say spin up is up direction considered as 1, and then you have to have it 0. This is anti-ferromagnetic, and you will have to propagate the data throughout. And you want the same data at the end, right? You want to have that number of nanomagnets. There is a calculation to do the ferromagnetic and anti-ferromagnetic. Ferromagnetic is just it propagates the same data. Anti-ferromagnetic is like inverted. It's like an inverted, what you call in this terminology, zeros and ones and 1 to 0. This is the first basic principle which everyone must understand when you are talking about nanomaterial logic. So next. This is a majority logic gate. This one is one majority logic gate, and these all three represents the same majority logic gate, but there are few differences we can notice, right? Same majority logic gate in 3 different ways. Why it is? All does see it's 0, it's 1, and it's 1. So what this will give it here as a majority, whatever we are having 1 here, it is connected anti-ferromatically. So what it will give? 1 gives me 1. Anti-ferro. 1 gives me 1. Yes, right. 1 gives 0 in the anti-ferro, right? So this is counted as 0 here, and 0 gives me 0 in the ferro, and this 1 gives me 1 in the ferro. These are connected ferromagnetically, right? This middle dot is the majority logic. Okay, you are having 3 inputs. This 1 gives you 0 here. This 0 gives you 0 here. That's ferro. This 1 gives you 1 here. So what is the majority? 0 is the majority, right? 1 gives 0 and 0 gives 0. 2 zeros, you get a majority 0. That is here the majority logic. And you want to invert it, what it does? You put it one more anti-ferro. 0 gives you 1. Simple. 4 years of PhD you understood in one slide. As that simple, right? Majority logic is different, so simple. And what is the differences between two? Here I am placing it this way, here I am orienting the angle. Right? If it is this and this, what makes difference? Lot it makes difference in the nano. When you disorient this angle for this 45 degree, right? You get this unidirectional signal flow on the focus field and low energy for switching compared to this. When you want to move in the horizontal, you can travel into this 45 degree. And here, oh, I see no such things here, but the shapes are different. Why? These are standalone input nanomagnets. This oval shaped input nanomagnets, right? It cannot by itself, it cannot be orienting either towards 0 or 1. You need an external energy driver nanomagnet to do that. But when you have a slanted edge nanomagnet, right? It is a standalone input nanomagnet. You need not have an okay. Still might be okay. Great. You need not have this input driver nanomagnet, but rather you can have this pins oriented here. So next slide, sir. Okay, another 10 minutes I will finish. Huh? Don't worry, I'm on time. This is how it works for the majority logic. When you have these are the 8 truth table entries. I think most of you are aware of the second semester, right? You may be aware of these truth table entries. how does the magnetic logic work. So these are all the 8 truth table entries using using this magnetic logic. This is how the universal magnetic logic is to perform this NAND not truth table. So that is called this magnetic logic, universal magnetic logic. So using this we can define anything, multiplier, adders, and so forth. Next slide. Yes, one slide previous. Yes. So here we are talking about this magnetic logic, right? And one group from Sanjita Banja's group from published in Nature Nanotechnology from University of South Florida. They have envisaged to use this nanomagnets for this processing, like magnetic co-processing. They attempted to do image processing using this edge detection, using this magnets placed in order. So that is the first key step towards this having magnetic co-processors or a processor in reality. So that's what the research is going on. So next slide. As I said, we have to start from magnetic logic to adders, and you can rightly see from the next slide how these adders have been evolved. So next, all does the same thing of an addition, but you can see how throughout the year it has evolved. Next slide. Next slide. Yeah, finally it boils down to this. That is the state of the art, and you will be seeing what further it can do to the state of the art. So next slide. So this is some theory. What we are going to focus. We are going to focus on 3 things. Area efficiency by reducing the number of nanomagnets. As you saw from 59 nanomagnets, it came to 17. And we reduced it further down, right? And speed efficient and energy efficient. When area efficiency comes into the picture, everything on top of it is an added advantage, right? So next slide. Yeah. So this is what we have been seeing, right? In 2017, we had 19 nanomagnets. And in 2020, what we had is the same functionality can be used using only 4 nanomagnets. We have break down the entire addition into only 4 nanomagnets, 1 bit addition, right? When you want to go for a 64-bit addition, having 20 into 64 bits design is enormous. But when you have a 4 nanomagnets performing the same function, that's what we teach the area efficiency, energy efficiency, and speed efficiency. Does it make sense? Thank you. The next slide. So we have been contributing towards convolution architecture. So everybody knows here what, or everybody wanted to know what convolution is. Basically, it's a sum of products, right? This y is equal to x0 x0 plus x1 x1 plus x2 x2 plus x3 x3. That's an example. It can write simply on a paper like this, but this has a very, very brief thing as described. It has enormous, see, you can break down the multiple blocks, right? Multipliers and adders, and even for the multiplier block can be broken into adders and logic gates, and everything boils under the adder design. That's what we made a specific contribution to the adders, so that can be reused in all of these blocks when contributing for a bigger picture like convolution. So having a 4 magnets performing an adder design for a convolution is not in any way equal to having a 29 nanomagnets or 1 bit adder performing for a convolution, right? When you talk of adder, 490 may not be much difference, but when you see this block diagram in bold, that makes a bigger difference when we are competing with the technology CMOS, which is now in 3 nanometer mode. We are a long way to boil down to that 3 nanometer or whatever it is, but now we are concerned more about energy efficiency. Is that making sense? Now on a broader picture, we are not comparing with CMOS anywhere on area efficiency, because CMOS is already on the 3 nanometer, and we are talking about few hundreds of nanometers. But we will be down there, and when that is down, we have to be have an optimized design with the reduced number of nanometers. Size can be 300 meters years ago. This is the bigger picture what we want to contribute. So how much time I have now? So 10 more minutes.
Yes, sir.
Yeah. The next slide. So this is the very quick summary of what it is, right? So now you see, first I presented a universal magnetic logic gate, and then I proposed an adder, and then we had a different type of adders, how we contribute. And there are like, to perform 8 truth table entries, people used to use 8 designs of adders. It's not like one design can be reused. It requires 8 different designs. We try to optimize it using only one design. We can reuse it to perform all the 8 truth table entries of the universal magnetic logic gate. And then when you are talking about this approximate nanometric level, what is this approximate computing? First thing you are getting, right? So there was a missing the slide earlier. Approximate computing is like we are talking about this energy efficient computing. And not all time you require 100% accurate results. Many of you who have been working or wanted to work on this image processing algorithm, right? You know, 100% accurate is not required for many of the applications and many of the programs. That's where approximate comes into the picture. You get a 70% output right, but with the reduction of area, millions, multiple. So that is the key thing what we have to harness. As we are talking about this energy efficient computing, right? We wanted to cut down that aspect also. So we can also take this adaptive computing from the beginning, where we can target applications where the 100% accuracy is not needed. And now all boils to one. Only one majority gateway. As you have understood from the first slide, you need 3 inputs and 1 majority logic output. That gives you a majority logic, right? It gives zeros, and ones, and 3 nanomagnetic inputs and 1 nanomagnetic output. 4 nanomagnets gives you a majority logic. Now, after performing research for years, we have come up to a state that majority logic, whatever we are talking about, 3 inputs and 1 output nanomagnet, gives you a 1 bit addition. That's what we have shown. So that is the summary block. When it starts with the universal logic gate and it's boiled down to the universal logic gate, but its performance are comparable. And this is also performs all the 8 to 10 minutes in the operation. So this is where I like to end the presentation. So we'll take quick queries. Next we can that. Yes, we have been talking about this the whole picture, right? We have been talking about the graphene, integration, standardization, nanomagnetic logic, and this approximate computing. And with all this demonstration of the case building blocks, we are looking for a bigger goal of having this power handling layer building this magic problem. That is a bigger help. And next year. Final outcome what we are trying to do. We are trying to have this graphene nanopatterning, this ID measurement characterization, and we are developing this parametric modeling process. And we are having this deep generation for the current reports, and we are using this next micromatic simulation tools, where we also need to have a power planning, as I said, as on-chip plug-in integration, replacing copper with graphene, and architecture development using FPGA, which finally boils down for these applications in research and scheduling. This summarizes the whole talk which I wanted to present. I believe I made it to 70% you are clear with what the technologies are and that we are getting to, right? Yes? Thank you. You are a good audience, huh? Post lunch session, really it worked well. Thank you.
Now the session is open for question and answer. Anyone?
Yes.
Please raise your hand.
Sir, I have one doubt. Sure. Yeah. You have shown your spin demonstrates something happens in copy and copy. Yes. How precisely we get spin up and spin down? When we drop 1 mole of copper, yes, then we get Avogadro number of unpaired electrons. Sure. It is the order. Yes, yes. How precisely can we get the accuracy of spin up and down states? Yes. So that was the key thing that group was trying to approach from this National University of Singapore. They have been proposing that bow-tie schematic to use this graphene bow-tie scheme to perform logic computations. And they wanted to have this logic computation when you say that they are doping it with something else, copper or whatever it is, that is depleting the properties of graphene. It is not actually the intrinsic magnetic properties of graphene. That's where the key thing which we have started working on. We do not want to have any dopants or any vacancy affecting the intrinsic magnetism of graphene, but we wanted to have a tuning parameters which by default will tune. That is a tunable parameters where we brought in the G and P in the same bow-tie schematic. That model was developed, but it was not proceeded further. Yes, due to its own limitations. Okay, sir. Thank you. Can students come forward for queries? Pose some questions.
in computer architecture, design, memory, graphing memory based, magnetic based architecture.
Sorry, what are the issues of dielectric breakdown or electrical breakdown?
Yes, sir. That's right. When we have this graphene nanoparticles for the 300 nanometers, close down to, we want to boil it down to say 50 nanometers. That's also the goal. And it happens to be at 1.2 volt. When you have this, all happens at the same breakdown voltage. And that was the issue we faced. That what could be the parameters behind that? Is temperature playing a key role there, or the width depending, right? When you come break down this to 50 nanometer and we are having a nanodot of 3 nanometer size, it also falls into this quantum confinement. And there is a key thing, temperature playing a crucial role there. And we try to model that parametric development using these answers and try to see how this temperature can be a key thing, which can also be tuned so that we do not get that interference when you boil down to the end of it. That was a good question, sir, and that was a key problem which we faced, which can be considered.
And one more,
Yes.
suppose something goes wrong in the logic.
Yes.
How do you troubleshoot?
That is the $1 billion question. And there is a CAD technology we are trying to develop, and a lot of other groups also can develop. All we are talking about so far is about this adder, 1-bit adder. But when you want to have a block of convolution, it has to be interconnected, either by a software or at least in terms of a software, at least in terms of a software, there has to be a thermal management called power planning architectures. And there has to also be a fault tolerant mechanism where when not any of your bits are supposed to be turned to 1, it did not turn to be 1. And there also another trick in using this approximate. It provides a better efficiency. Great. So you are following up throughout the presentation actively. Good. So this has two different parts, right? You need not integrate both of this. See, fluctuations of nanodots and in dipolar coupling, the coupling strength between the magnet A and magnet dot B is low. And when you wanted to bring it down to the 50 nanometer size, right, it will go abnormally. It will not stay in any position. It will call it a metastable state. Thermal fluctuation, switching of the probability error, it will keep on fluctuating. It will not fall into any place. So you in dipolar, you cannot go beyond below 50 nanometers. If you want to perform something in dipolar, you have to stay above that. Okay, one thing. And if you want to perform lower dimensions, right? You wanted to explore other interlayer exchange right? Interlayer exchange coupling. You want to go into that, where that coupling strength between two nanometers is comparatively stronger than the one in the dipolar. So here the thermal fluctuations will not come in. It will not randomly disorient itself either up or down. It will be in a predefined state. And here, how graphene links here is, it's like an underneath material. It has nothing to do with the fluctuation of the nanomagnet. It is to energize the nanomagnet. Rather, right? It is like an energy clock circuit. Like you have your wire connecting it to bulbs, right? You're having a wire. So this acts like a wire, which can energize the nanomagnets on top of it. Fluctuation problem is basically from the coupling. Here? Yeah.
Yeah, no questions?
Thank you, our wonderful audience. Huh?
Thank you, sir. Thank you, dear Dr. Santosh, sir. He has enlightened us a roadmap for devices and systems beyond CMOS. And while computing with magnets is important, and if we can talk about a small domain in the ferromagnetic material, how it is going to helpful for the arithmetic and logic unit, which perform all the arithmetic and logic operations in terms of adders. Okay, sir has explained and given us a elaborated explanation about all these concepts, starting from a 10 to the power of -9 scale to macroscopic. So it's very wonderful session, sir. Thank you very much. Sir.
So this is my dear students and participants, we are quickly starting next session also. It is the IT one, invited talk one by Dr. C. Thirumal Reddy garu.
Up to what time?
It's from 2:30 to 3:30. This is the session. After that, we get a tea break and networking. It's nothing but the interaction of the students and participants with resource persons. We start now. Invited talk one by Dr. C. Thirumal Reddy, Assistant Professor of Physics, Center for Nanoscience and Technology, Department of Physics. His talk is on fabrication of nanomaterials by hydrothermal and ball milling techniques. Let me introduce the speaker first. Dr. C. Thirumal has completed his PhD in 2016 from IIT Madras. Subsequently, he has done his postdoctoral research at IIT Delhi in 2016 to 17. Currently, he is working as assistant professor in VNRVJIET. His research interests includes ferroelectrics, piezoelectrics, magnetoelectronic nanocomposites, ionic polymers, and so on. He has published 23 research articles in peer-reviewed, well-reputed international SCI journals and was granted with a patent also in his name. He also presented his research work at various international and national conferences. Currently, he is working on two funded research projects. One is by DRDO under consultancy basis worth of 10 lakh rupees. Another one is by DST Cell in collaboration with Central University in Hyderabad worth of 18 lakhs. And he is the IEEE coordinator for VNRVJIET chapter. Sir, welcome, sir. And he is the coordinator for this summer school also. It is the coordinator's talk. Welcome, sir. Let's give him a big round of applause.
Yeah, very good afternoon, Vanna. So I feel this is my class. So let me continue like that only, so that more exploration can happen. Because most of the participants are students, it will take you from basics to advanced level. Okay. So yeah, I'm Dr. Thirumal, working here at the VNRVJIET from 2017. I just completed my 5 years of experience at VNRVJIET. And yeah, please go to the next slide, sir. When we talk about nanotechnology, we need to understand what is this nanotechnology. We need to realize the dimension of this nanotechnology, right? Nano means how much it is? Can anybody tell me? Nano, 10 power minus 9. We're discussing about the length scale. So nanometer means 10 power minus 9 meters, right? So let us see how can we visualize the nanometer in reality. So till now we have seen the lectures by eminent speakers in the cutting edge technologies in nanoscience and technology, right? Like nanomagnetism, spintrons, etc. Now let us see how one can realize or how one can understand the nano actually. Okay, let us see a beautiful video which I have taken from YouTube. Whenever I go to my classes, especially when I'm talking about nanotechnology, I show this video. Definitely, it is going to give you a feeling of what is exactly the nanometers. Please click on that, sir. Please click on that.
This one.
Great.
ఇందులో రావట్లేదు వీడియో రావట్లేదు పీపీటీ మోడ్ లాగా ఉంది
ఆడియో
అసలు అక్కడ రావట్లేదు సార్ ప్రాజెక్ట్
share entire screen, sir.
పీపీటీ షేరింగ్ లో ఉంది ఇది దాన్ని మినిమైజ్ చేస్తే స్క్రీన్ షేరింగ్ మోడ్ పెట్టు
Yeah, please try to see the video. There is also a scale bar at the bottom. You try to see the scale as well as the video. Then you really actually understand what we are talking about, what the dimension that we are talking about. Okay. Because this is a training session, at least by the end of this day, the participants who are there here, they should understand what you are talking about, at what scale, at what dimension we are talking about. They should have some reality. You should have to realize it.
మళ్ళీ క్లిక్ చేస్తా సార్ ఇక్కడ చేయండి
అక్కడ సార్
దీని మీద సార్ వీడియో సార్ వీడియో లింక్ హైపర్ లింక్ కదా
సార్ చేసేసి వీడియో ఆన్ చేయండి ఫోల్డర్లో ఇది ఆన్ చేయండి ఇది షేర్ చేయండి
అది ఇన్పుట్ మోడ్ మార్చాలి
వీడియో కష్టం సార్ ఆడియో
షేర్ చేయండి సార్
కాదు సార్ ఆడియో రావట్లేదు
ఆడియో వస్తుంది
ఆడియో అవసరం లేదు జస్ట్
ఓన్లీ వీడియో స్క్రీన్ షేర్ చేయండి
Yeah, please play the video, sir. Students, all of you please observe the video and see the scale that is available at the bottom. We are at 1 kilometer height, 10 kilometer height, 100 kilometer height, 1,000 kilometers, 10,000 kilometers, 100,000 kilometers, 1 million kilometers, 10 million kilometers, 100 million, 1 billion kilometers, 10 billion kilometers, 100 billion kilometers. You can see what is happening, right? I hope 1 trillion kilometers, 10 light years, 100 light years, 1,000 light years, 1,000 light years, 100,000 light years, 1 billion light years. Different galaxies are coming to each other. 10 million light years, 100 million, 1 billion light years, 10 million. Now we're coming back. Okay. From there we're coming back and see what is nano. I hope it is visible, right? You can see 1 millimeter going down, 100 micrometers, 10 micrometers, 1 micrometer, 100 nanometers, 10 nanometers. The morning two sessions, they were talking in the range of 1 to 10 nanometers. Okay, you can see we are at 10 picometers. I hope you realized what the dimensionality we are talking about, right? I hope this is clear. So we are talking about 1 nanometer means we are almost nearby an atom. So atomic level people are talking. Atomic level people are able to manipulate the materials. That is the technology that we are talking about today. Okay. Please stop the videos. This is a video that will give a realization about the dimensionality about nanotechnology. Yeah, you can see here, started with 1 centimeter. One Einstein is about 100 micrometers, and one bacteria is about 1 micrometer. One virus is in order of 10 to 100 nanometer, and one molecule if you take is about 1 nanometers. So we are talking about 2 nanometers, 3 nanometers means we are talking at the molecular level. So we are arranging the molecules to get the desired property. Okay. So this is to understand what exactly the dimensionality we are talking about. Next, please. Yeah. Why we are interested actually in this nanotechnology? If you take any material, whatever you are touching, and grind it in a grinder, whatever the best grinder that is available to you, and the minimum particle size that you are going to get will be in the order of 1 micrometer, let's say. Okay, that means this all the materials that you are touching, they are made up of with microscopic particles in the order of microns. So you are getting the property whatever you see. The strength of the material may be the conductivity or resistivity or optical emission, the light emission, whatever the property that you take, that is because of the particle size that we are having today. But when you further reduce the particle size, what happens? There are two things are going to come into picture. One is increased surface to volume ratio. That means if you take, for example, you take a cube and divide into 4 pieces, equal pieces. Okay, and you try to calculate the surface area of the initial big cube and the small cubes. What happens? Can anybody imagine? The surface area will increase or decrease after making into 4 cubes. The total surface area I'm talking about, total surface area of the 4 small cubes, will it be greater or smaller than the big cube? It will be greater. That means by essentially by decreasing the particle size, the first important property that is going to come into picture is that increasing the surface area of the material. That means now the particles are having lot of contact areas with their neighbors. Okay, because we have enhanced the surface area. Because of that, what is going to happen is, you know the fundamental chemistry, right? So when you have lot of neighbors, then what happens? The reactivity will increase. The rate of reaction will increase, isn't it? Like that, there are properties are going to be enhanced. The strength, the bonding between the particles is going to be enhanced. The strength of the material is going to be enhanced. That is the reason why nowadays people are using the nano cement. Initially, the cement that we are using today, the minimum particle size will be around 10 to 20 microns and so on. But now people are trying to develop these nano cements where the 10 micrometer particle is going to divide into, it's 1,000 times. We are going to into nano scale. So that kind of nano cement is going to enhance the strength. Like that, the properties are enhancing because of this increased surface area when you decrease the particle size. That is the first fundamental thing. A beginner should understand why these nanomaterials are actually showing a peculiar or enhanced properties. Okay, this is one thing. And second one is very, very interesting is there is a new phenomenon is going to come into picture when you come down the size of the particle. That is called quantum confinement. For example, I will give you a simple example to understand this quantum confinement. For example, there is a cubical box is there. I am sending an electron into this cubical box. This electron is having the freedom to move everywhere. That means it can move in 3 dimensions. Therefore, in the bulk materials, when we talk about the micron particles, electron is having 3 degrees of freedom for their motion. Okay, but when you are cutting down, for example, I am cutting down my cube. Next, please. Yeah, I am cutting down my cube into slice. That means I am cutting down, let's say, Z axis. Along Z axis, I am cutting down. You got a slice, right? In the slice, how many directions my electron can move? In the plane, how many directions electron can move? Only 2 directions are there. It can go either x-axis or along y-axis. Isn't it? X and y are there, but Z is cutted off, right? Now only plane. Now that means we are restricting the motion of electron from 3 dimension to 2 dimension. Understand? So basically, how the properties are coming, your electrical conductivity or resistivity, whatever you know the properties, that is because of the motion of electron, the behavior of electron in a given material. So we are changing the behavior of electron. We are restricting the behavior of electron into 2 dimensions. That's why we're talking about. This is called thin films, or quantum wells. Quantum well means the electron can move only in 2 dimensions. The second one, if you take quantum wires, now you're cutting this slice, this plane into, again, you're reducing the size along one direction. Let's say you're reducing along y-axis again. Then what you get? Basically, you get a thin wire. Isn't it? Now, in thin wire, in how many directions can electron move? Along wire means it can move only 1 direction. That means we are restricting the electrons to move only in 1 direction. Now you see the behavior will change, the conductivity will change, the optical properties of the material will change, everything. Everything related to the electron behavior will change. Isn't it? Every property associated with electron behavior will change. The point clear? Now we are cutting down this wire into again along x-axis. What do you get? You got a dot. That is called quantum dot. What is it called? Quantum dot. That means in quantum dot, electron cannot move anywhere. It has to stay there only. We are restricting the motion of electrons. Isn't it? You see, the property is going to drastically change. I'm going to show you some of the important applications of this particular quantum dots in the coming slides. So I hope you got some idea why these nanomaterials are so important. Because when you are reducing the size, the surface to volume ratio is going to be increased. That's the one thing. The second one is we are able to control the electron's motion, and hence we are able to manipulate the properties. We are able to increase the properties. We are able to control the properties of the materials. Because of which you are actually enjoying this, whatever the nano devices that are going to come. That are already there, some of the devices are already there. Okay, now the 2 fundamental aspects related to the nanomaterials when you talk about the properties, why they are so different from the bulk materials. When I say bulk material, the minimum particle size will be in the order of microns. When I say nanomaterials, the particle size of the particular material will be in the order of nanometers. Next, please. So because of these 2 phenomena, we are going to see the changing of properties, physical properties. For example, melting point. You have studied the melting point of a given material is constant, right? If you are going to decrease the size of the particle, it's not going to be constant. It's going to be variable. That means we are able to control the melting point. You see, just by changing the size of the particle. Similarly, chemical properties, reactivities. This I give an example, right? If you are increasing the surface area, the number of atoms, the neighbors will increase, so that the reactivity will increase. Isn't it? Next, electrical properties. You may think that the gold is conductor in the bulk level, but if you go to nanoscale level, it may not be the conductor. It may behave something. It may give some different properties of conductivity. Like that, every property is going to change at the nanoscale. That is the reason why in the morning I told there is a plenty of room at the bottom, given by Richard Feynman. That means there are a lot of opportunities to be explored. So this is the technology that is getting evolved. Started maybe 15, 20 years back, this nanotechnology. They started understanding the basics. Now people are able to develop the devices based on these nanomaterials, right? And coming to this mechanical properties, as I said, the strength is going to be increased and it's going to be lightweight. Understand? Lightweight will increase the strength. You see how many applications will be, isn't it? And optical properties. So if you see the gold, okay, no? Gold, what is the color of the gold? It will be some yellowish color, right? Okay. Have you seen any time pink, red or pink or blue gold? Not colored gold, the pure, you know, this is 99.999 pure gold in pink color. Have you seen? I will show you now in the coming slides. Okay. So that is what the properties, optical properties of the material will change when you are going to decrease the size of the particle. So this is why we are going for the nanomaterials. Now, when you, okay, this is science. These are the two phenomena that are taking place to change the properties and so on. So how do we produce? How do we fabricate such nanomaterials? Got the point? How to make a particle which is having how much size? Let's say 1 nanometer to 100 nanometers, below 100 nanometers. Typically, when you say nanometer means the particle size should be less than or equal to 100 nanometers. Okay? When you say nano, it should be less than or equal to 100 nanometers. So, how do I make such nanomaterials? That's the important question, right? Isn't it? If I want to make, let us say, this particular device, I can easily handle it with my hand. I can make whatever shape I want. But the nanoparticle, I cannot see with my eye. But I want to make a nano flower like this. Understand? What is the technology that you have to use so that you may have seen microscopic objects, right? In some movies, you may have seen microscopic objects. But I'm talking about not micro. I want to make a beautiful flower like this. You see? At the what scale to the at nanometer scale. That's what we are going to do in this particular session. We are going to fabricate the nanomaterials using two methods here. The remaining methods will be covered in the next sessions. I'm going to cover the basics of these two methods. But of course, you can explore more about these methods if you are really interested. You can come to our lab and we'll show you how to make these materials, nanomaterials, using these particular two methods. Okay? First one, now there are two methods actually. One is bottom-up approach. The second one is top-down approach. For fabricating the nanomaterials, we have two methods. In the bottom-up and top-down. What do you mean by bottom-up? For example, nanomaterial is a particle consisting of some number of atoms. Okay, right? So I have to join the atoms together so that I will get a ball. Laddu, you know laddu, right? Everybody know laddu, right? So like that, I am trying to arrange them in a particular manner, right? So that the ball size, the particle size will be less than 100 nanometers. The point clear? Right? So that is bottom up means we are starting from an atom and then slowly building up this nanoparticle. From bottom, we are increasing the size. That's one way. The second way is I will take the microscopic particle. Like already available particles is there. For example, you take let's say iron. Okay, iron. If you take 1 micrometer particle, I want to make iron nanomaterial. Let's say 2 nanometers nanoparticle how to make. What I have to do? I have only 1 micrometer particle. I can cut it out, right? I can cut it down into let's say 1,000 pieces. 1 micrometer I can make into 1,000 pieces. How do I make it? 1 micrometer, how do I make? That's where we are going to see the second method of fabricating the nanomaterials. So one is bottom-up approach, second one is top-down approach. I hope you understand, right? In bottom-up approach, I'm going to discuss about something called hydrothermal method. Okay, no? This is something like chemistry and physics involved in this particular method. Okay, if you are interested in fabricating the nanomaterials at your laboratory scale with let's say 30 or 40,000 rupees, if you want to make some gold nanoparticles or silver nanoparticles, you can able to make it at your home. So this is the method, important method we need to introduce to the beginners who are going to understand the nanotechnology. In this particular hydrothermal method, I am going to discuss about introduction to hydrothermal method, the principle, the different types, how do we control the shape of the nanoparticle, how do we control the size of the nanoparticle, what are the controlling parameters, followed by the different what types of materials we can generally prepare using this method, and followed by what are the advantages and disadvantages of this method. Yes, sir, please go to the next slide. Yeah, about the hydrothermal, if you see the history, it started around in 1845. Okay, now people are trying to develop artificial quartz crystals. Artificial quartz crystals. Okay, why these are? Because quartz crystals show some electricity. They want to use in some electrical gadgets. That's the reason why they wanted to actually fabricate these quartz crystals. For that purpose, they started artificially making this quartz crystal using this hydrothermal method. It started way back in 1845. They used to blow the crystals. You know crystal, right? Have you seen diamond? Diamond is a crystal, right? Like that, if you want to make some crystal artificially, what are the diamonds that you are using outside? So most of them are artificially made. Okay? You can make the diamonds in the lab. So using this kind of hydrothermal methods, etc. Okay? Now you can see here, and after Second World War, people realized that there is a huge demand for quartz. During Second World War also, people, actually some countries are having lot of quartz and other countries are not having, because quartz is very essential material for making electronic instruments. If they want to participate in war, they need some electronic instruments, isn't it? How do we make that? For that, the technology used by them is only quartz crystals are there. But how do we artificially produce these quartz crystals? After the Second World War only, the importance of making artificial quartz crystals have came into picture. Later, in well laboratories, okay, na? Yes, please. You can see this is the principle of hydrothermal. What do you do in hydrothermal? It is very simple. You might have studied in chemistry, right? You want to make one product. What do we require? For example, I want to make, let's say, NaCl. What do you require? I want to make sodium chloride. What do you require? Sodium and chloride in simple parts. Okay. But as it is sodium, I cannot take and react. I can participate in reaction, right? I will take maybe some. What do you take? Sodium hydroxide. And I will take some, I think chemistry, somebody is the expert. HCl will take, isn't it? So then we will get, we'll take some A, add with B, there will be some reaction, we'll get the product. The same principle is valid everywhere. Whatever the technology that you take, the principle remains same. We need some precursors. A and B are known as what are the precursors. These precursors we are going to take in a closed system. You can say there is a bowl, right? This bowl is called as autoclave. What is it called? Autoclave. It's like a pressure cooker. You know pressure cooker, right? Every day you'll be using in your home. Your mother will be using, right? So what you take, we take all ingredients in that. We close the pressure cooker. Then we heat it. That's what exactly we are doing here in hydrothermal. You take two reactants or the precursors and dissolve them in aqueous solution. Like, because this hydrothermal means this is happening in the presence of water. The solvent is here water. You can also do other solvents, which is known as solvothermal process, which is again the similar process, but instead of water what you do is you use other solvents. That's only the difference. Here, what we do is we take our precursors, dissolve in a particular solvent or water, especially here, then close this. This is white color is Teflon, medium of Teflon, and this Teflon bowl will be actually inserted in a hardened stainless steel. This is stainless steel. Actually, this is concentrated cylinders. This Teflon will go and sit in this cylinder. Then in this Teflon, we are going to take the precursors along with water, which is already dissolved. This precursors are dissolved in that. Then close this tightly. You know pressure cooker, right? Let it close it tightly, properly. Okay? Like that, we have to close it. Then what we are going to do? We are going to increase the temperature using conventional hot air ovens or microwave ovens. You know already microwave, right? Microwave oven you can use or conventional hot air ovens also you can use. Anything is fine. Then what I can see is, you can see the precursors which are present in the water, they are going to react. Then the product will be formed. But here, if you see, this product is going to form, okay, above the critical temperature of water. But means what? Above the boiling point, you can take, especially most of the times it will be happening above the boiling point of the water. That means they're having superfluid states. The precursorrs will be having in superfluid state within this enclosure called autoclave. In superfluid state, they are going to react. Okay, na? And after the reaction is completed, when you actually cool down the temperature of this particular autoclave, these reacted products, they are going to crystallize. Have you read crystallize? You know crystallize, right? Crystallize means from the superfluid state to they will come to solid state. While coming to solid state, the atoms of this materials will arrange just like this particular row. Arrange, atoms are arranged regularly, isn't it? Like that, each and every atom will be arranged. While they're cooling down, this is called actually crystallization. Cooling down, atoms will be arranged regularly. Then, after cooling down to room temperature, open this and see what will be there. There will be some solution with some precipitate. Now, what we have to do is we have to take this precipitate and we have to actually separate the precipitate and see the size of the particles that you got. The precipitate, we have particles, right? How that you get? Then see the size of the particle using the high-end electron microscopes. Then what you'll be getting is, next please. You can see here the particle size. This is around the 100 nanometers, right? And see the particles. This compared to get 7 nanometers. Compare this particle size with this dimensional thing. It is less than 100 nanometers. The particles are having less than 100 nanometers. So using this particular hydrothermal method, one can grow the crystals. Initially used to do. I told you used to grow the quartz crystals and gems, etc. Now people are using this extensively for producing the nanopowders. Okay, next please. So there are two different methods in hydrothermal. One is to take this autoclave. You can create a temperature gradient across this autoclave. Generally, this method called temperature difference method, which is used to grow the crystals. Okay, it is used to grow this whatever the gems you are having, your ring, that will be grown by this method. Okay, artificially in the labs. Now look at this. If you have temperature gradient, what happens is here the bottom we have the solution which is at high temperature. Then this is going to be evaporated. The vapor state they're going to the top end, and here we have at a low temperature. At the top we have low temperature, at the bottom we have high temperature. When it is going from bottom to top, there is a temperature gradient. So this gradient will make this particular vapor to condense, where there is a small seed crystal. Already we kept a small seed crystal. Now this vapor is going to crystallize on seed crystal, so that from small crystal to it will make us to grow as very big crystal. Then you can cut it and use it for your purpose. So basically what we are doing, we are heating the solution to superfluid state, and we are actually transforming from high temperature to low temperature region. Then we are trying to crystallize at low temperature region. So this is one method to grow the crystal especially. But here today we are not talking about the crystals, we are talking about nanomaterials. So next please. In second method, next please. In second method, what we are going to do is we are going to make actually the nano powders, nanomaterials. Okay. So this is going to happen in a isothermal way. Isothermal means what? I hope everybody know what is isothermal, right? Where the temperature is constant. That means across this autoclave, I am not going to maintain the gradient. Instead, it is going to be a constant temperature. Then you heat it at high temperature, make the superfluid state, and slowly, gradually you decrease the temperature. While decreasing the temperature, you will get precipitation at the bottom of the autoclave. You separate it, then try to understand its properties. So it's simple, right? But there are a lot of parameters that has to be optimized, that has to be controlled. You can see here, and these are flowchart shows how we make hydrothermal method. the solution configuration, you may require reagent process and transfer the solution to the reactor or article. Then you have to actually give the some temperature, and finally you have to wash. You need to separate the powder and wash it, then dry it. Then you get the particles to the order of nanometer. So you told about different flowers I can make. How can I make? I'm going to explain that the shapes and the size. How do we control? Next, please. Here are the controlling parameters. You take any material that's prepared by any technique that is available on the globe. So generally, we need to consider the thermodynamic parameters. The only thing that can control the shape and the size of the particle are the properties sometimes. Only those are pressure, temperature. These are the important parameters one need to understand, one need to control. If you control these parameters, then actually what you can do is you can actually change the shape, can change the size along with the chemical properties. That is important: temperature, pressure, and the time. How much time you are heating. And here we need to understand when you are heating some solution in a closed vessel, what happens? A closed vessel, you are heating some solution. What can happen? What can increase? Pressure can increase, right? That's what the pressure cooker says. Isn't it? Isn't it? So look at this phase diagram. This is the pressure, this is the temperature. How much amount of solution that you have to take in the autoclave? Okay, no? That you will decide how much pressure will be developed at a particular temperature. Sometimes you might have read in the news the pressure cooker have blast. Isn't it? Sometimes happens, right? Why it is happening? First thing is that whistle may not be working. It may be going not. It may not be going down. It's stuck there, and they have might have filled the pressure cooker till the top. Okay, top of this pressure cooker. Then what happens? You see, for example, you have filled the pressure cooker with 90% of whatever you want to cook. Okay, na? See, even at low temperatures, they're creating how much pressure? Hundreds of atmospheric pressures. The point here, you can see here, for example, I am filling my pressure cooker only with 10% of material. Isn't it? Autoclave is filled up to only 10%. You see, even when going to high temperature, there is a gradual increase in the pressure, not sudden increase in the pressure. So you always have to control, you have to see. When you are working with this method, this is a precaution. If you have the knowledge, what is the temperature range you have to work? How much amount of the liquid you have to take? For example, in my lab, I have a autoclave of 25 ml. Okay? I cannot fill 25 ml. Isn't it? How much I have to fill? I can fill maximum of 30% of the 25 ml. Okay? Then I can increase the temperature slowly, then pressure will increase gradually. Then I can control it. If I take 90% or 80% and if I apply finally what happens? My autoclave will blast. No, not right. So this is the key notice, and one need to understand temperature, pressure versus temperature for a given percentage of filling in the autoclave. And the same principle applies you at your pressure cooker also. You can teach your mother or who is cooking newly. Okay, now they should know this principle. Right? Next, please. So what are the types of materials one can actually fabricate or the synthesize using this hydrothermal method? You can actually fabricate metallic nanoforms. That means you can fabricate metal nanoparticles. Gold, let's see here. Gold, platinum, silver, cobalt, nickel, etc. See, I told you, this is actually gold. See, from orange to violet to pink. What is difference? The difference is difference in the particle size. Somewhere it may be 5 nanometers, somewhere it may be 10 nanometers, somewhere it may be 15 nanometers, like that. When you are changing the particle size, what happens? If you are shining the light, the scattering will change, right? When the particle size changes, the scattering will change. Isn't it? and the reflections will change, absorptions will change. That's how you are getting the beautiful colors. No. So these colors of very, very important. In olden days, we could use these colors, gold colors, different colors for painting. With gold nanoparticles. They use for painting also. So now you can see how the optical properties, optical emissions are changing when you're changing the nanoparticle size. And here you can see the different shapes. Here they are looking like rods, here they are looking like particles. When you're changing this shape, again, or changing shape or size, we need to optimize the parameters, temperature, pressure, time, and the chemical precursors, etc. We have to optimize. Then, for each and every experiment that you do, you have to check what is the morphology, means what is the shape of this particular particle. At this condition, what is the size I got? At this condition, what is the shape I got? Then, if I change this condition systematically, then what is the change that is going to happen? Like that, we need to understand the shape and size with respect to the controlling parameters. Right, next please. We can also make nanostructures of oxides, metal oxides, iron oxide, zinc oxide, zirconium oxide, etc. You can see here, this is the zinc oxide nanoparticles in different shapes. You see, nano leaves, nano flowers, nano rods, intermediate. What is this? Nanoparticle, you see? How spherical is their arranging? Isn't it? So, by changing the conditions, synthesis conditions, one can actually get this kind of nanoparticles, the nanowires, nanoplates, nanocycles, somebody makes nanocycle. Okay, na? Like that you can make. You can see the dimension. This is only 1 micrometer. So this will be, let's say, 100 nanometers, the width of this, diameter of this nanowire, right? Isn't it? I hope you got some idea how people are fabricating these nanoparticles or nanostructures at laboratory using this method. Is it right now? Still here? I hope you are following. Yes or no? Okay, next, please. Now, this shows some of the advantages of this hydrothermal method, which uses the low temperature. You can see this is this band, hydrothermal band. So different techniques one can use to prepare the materials that you are touching today. If you take your smartphone, hundreds of materials are embedded in that. Okay, no? Those materials are made up of either of these particular techniques. Where they are using any of one of these techniques to prepare that materials. Okay, no? Hydrothermal stands here, which generally use low temperature, okay, no? And low pressure sometimes. Next, please. If you see the advantages, the cost of the instrumentation, energy are less. It gives good control over particle size and shape. Okay, na? That's advantage, another important advantage. You get crystalline phases, and you can also create large crystals and high purity crystals. You can create using this particular hydrothermal method. Okay? Yeah. Next, please. And the disadvantage is everything is happening inside the pressure cooker. I cannot see what is happening, right? Isn't it? I cannot see the crystal growth. Whereas there are some techniques where you can actually see how the crystal is growing. Don't think that crystal will go just like that. In other conventional methods, you want to grow crystal, it will take months. Per day, it will grow only, let's say, 1/10 of 1 millimeter. Okay? Per day, how much it will grow? 1/10 of 1 millimeter. That's clear? So that much slow that it will grow. Because what we are arranging actually in crystal growth, we are arranging the atoms. We are arranging the atom by atom, right? That requires a lot of time. Isn't it? I cannot tell my atom, your bonds in there. They can sit, but they cannot be in a particular way that I want. Isn't it? If you want in a controlled way, it requires a lot of time. Right, next please. Coming to the second method, ball milling method. This is a top-down approach. This everybody knows. Milling means what? You know what is milling? You are eating this chapati, every day. From where it is made? Flour. isn't it? How it is made? By grinding. Essentially, what you are doing to make nanoparticles, you are taking microscopic particles and grinding. Okay, na? For grinding also we have grinding speed, grinding temperature. Okay, na? The amount of the powder that you take for grinding. These are the controlling parameters you can see here. Yes, please next step. I'm going to understand here. So this is a simple milling machine where people use outside to grind the materials. Here, in our method, we are going to use something called ball milling machine. Next step. Next. Yeah, this is a milling machine one can use where there is an enclosure in which we are going to take the powder to be fabricated in nano size. That means I will take the powder which is having, let's say, micron size particles. Along with, I will take some metallic or ceramic balls. Okay, na? Then I put it in this enclosure and I rotate this with high speed. You can rotate this in the about its horizontal axis and also about one another vertical axis. So in two ways you can rotate it. But essentially what is happening here is when you're rotating it, these balls are going to apply some impact force on these particles. Okay? And there will be also some frictional force between the balls and the enclosure. If between ball and this enclosure, we call it as the wall of this enclosure. Between the wall and ball, there is a particle that will be crushed into particles. So basically here we are using the powder along with the balls in the enclosure and rotating with high speeds. And the speed has to be optimized. Okay, no? There is something called critical speed where you get uniformity of the particle size and more good properties with the less defects you get with the critical speed to do it. You can see here, as you can rotate this about its horizontal axis and also about its, you can rotate like this also, right? That means about its vertical axis. Inside what are there? There are balls with particles. So there will be basically impact force on the particles by the balls and also attrition, means the frictional force between the wall and the balls. If the particle is there, that will be crushed. And this kind of method is used in the industry to fabricate large amount of nano powder. For example, if I want to make nano powder for my research, I may require maybe 1 gram or 2 gram to connect my research. But if I wanted to sell this nanoparticle, I cannot sell this 1 gram, 2 gram nanoparticle. I have to make, let's say, 100 grams, 1 ton, 2 tons. I cannot use the hydrothermal method for fabricating large amount of nanoparticles. Okay, so this is the method which will be used in the industry to actually fabricate the large amount of nano powders that we generally use today. The cosmetics, when I use cosmetic powders, right? Nowadays people are trying to make nano cosmetic powders. Okay, now? So even these powders can penetrate into your skin also. Okay, now? So these powders can be produced by this kind of ball millimeters. And again, controlling parameters. Everywhere, whatever you take, you can optimize the things, right? Here, what we can optimize, the speed we can speed. In the media means we are talking about the jar means the enclosure and the balls and their size. How much big is the jar? How much the size of the ball? Okay. Then what is the milling speed, milling time, milling environment? Are you using this direct powder or are you using any wet condition like influence of water or any other solvent you are using this particular grinding or milling? And milling temperature. Generally, when we are discussing about ball milling method, we are going to actually take the powder to ball to powder ratio somewhere between 10.1 to 20.1 ratio. 10:1 to 20:1 ratio you will be taking. That means more mass is given to what the balls. You do other way, they may not be crushed properly. Alright. Yes, next please. You can see here. These are the two methods. These are the two graphs or the two pictures. It shows the shape and the size of the nanoparticles using this ball milling method. So here the disadvantage is I cannot control the shape of the particle. Just grinding only. No, I cannot control. You can see irregular shapes are there. Isn't it? You can see I have given here one particular example from hydrothermal. You can see how spherically they are arranged here, isn't it? Whereas here they are not arranged that much spherically, right? But for some application, this much accuracy is fine. In that case, we can go with ball milling. But if you want to go for research level, definitely we require high quality and controllable shape and size for our applications. Okay. Advantage: inexpensive, large scale process up to 2 nanometers. We can produce using the ball milling. And disadvantage, as I said, irregular nanoparticles, introduction of defects. Because this is mechanical grinding, so defects will be there. And introduction of impurities from the balls that we are using or the container that we are using. Sometimes some impurities may be also added to the product. Yeah. Next, please. This is about the conclusion from these two methods. I have given some basic introduction how we are going to fabricate the materials using hydrothermal and ball milling methods. Okay, starting with principle and controlling parameters, how will be the particles looking like in each method. To give an overview about this. Is there any doubt, students? Sir, how much time I have?
5 minutes.
5 minutes. Can I go to 2 slides are there? So this is about how to fabricate the nanoparticles. But what I do in my research lab, okay? I generally work on actuators and sensors based on the piezoelectric materials. Sensor property based on the property that I am looking for. This is just preparing the sample. Any type of material you can prepare using these two methods. But after making the sample, what you are going to do? What is the application you are targeting? I am targeting the actuators and sensors used for robotic applications. Okay. Next. Just quickly go to the slides. Yeah, I use electricity. You know, electricity means, right? When you apply mechanical stress, it produces electricity and vice versa. For example, quartz crystal. This is the crystal which is known during World War II that it can produce electricity when you apply the stress. That is the reason why there was so much demand during World War II. Okay, next please. You can see here, just by applying the force is producing the voltage. Yeah, next. There are some different materials that we work in our labs to fabricate these piezoelectric materials. Next, please. I can see these different kinds of it's a crystal, powder form, and it is a thin film form of the piezoelectric materials. And where we use these piezoelectric materials, and this is not required. Next, please. Yeah, when we use these piezoelectric materials in robotic applications, in the actuator applications, and the sensing applications, you can see everywhere this particular sensors and actuators are used piezoelectric materials. Not only that, next please. We are now able to produce the electricity when the vehicle is moving. They are going to keep the piezoelectric actuators or the sensors within the types of the vehicle. When it's moving, some stress will be applied on the material, it produces electricity that will charge your vehicle. Self-charging vehicles, people are trying. Next, please. Yeah. This is ferroelectrics is one part of one category of piezoelectric material which will be used especially in memory devices. Today we are talking about memory devices, non-volatile, volatile, and all. So this is one of the important and status. The status of these particular important materials are they are already utilized in the non-volatile memories. If you open your computer, you can see. Please go to the next slide, sir. You know this. You can see ferroelectric memory company is there. These are used already in our computers. Ferroelectric random access memories. This is basically made up of ferroelectric. Ferroelectric means is one category of piezoelectric material. We are looking at in my lab. We are working basically to develop this memory devices or the memory device related materials and actuators as well as sensors. So I think I can conclude here. If you have any doubts, please let me know.
Thank you very much, sir, for your excellent and administration on the fabrication of nanomaterials by hydrothermal and bonding methods, including their advantages and disadvantages. You have covered topics like nanoscale world, and also you have given the principles of nanotechnology like surface to volume ratio increment in the nanoscale, and also quantum confinement. And you made our students and participants they got exposure on piezoelectric and ferroelectric materials and their applications in daily life. Students, the presentation is open for discussion. If you have any queries, please.
Please. Mike, can you pass the mic? I could be one bit.
Who is it? Please raise your hand. Is there anybody? You do. So there's one.
I hope you are in the auditorium, right? You are present here. Everybody present here, right?
Yes, sir.
Yeah.
Actually, while mentioning the ball milling method, while you are discussing about its disadvantages, you mentioned about some defects.
Yeah.
So, what sorts of defects you could observe?
Yeah, good. You take a stone and a hammer. Just hit the stone with the hammer. What happens? Can you get a regular shape? You get some kind of small pieces also, right? I want to cut into say 4 pieces, the stone. And it may not happen 4 stones exactly that I want. Just by mechanical, mechanical way, isn't it?
Yeah.
So that kind of surface defects will be found.
And while talking about parameters
Hmm.
like temperature and pressure, in hydrothermal method,
Yes.
the one more parameter which we observe in any research paper is that we maintain its pH value to be neutral.
What is it?
We maintain its pH value to be neutral.
Yeah,
So we make it, if it is acid, we'll add NaOH to make it to 7. If it is base, we add KOH to make it neutral. So what is the reason behind making the precursor solutions to be neutral?
It's always may not be neutral. The first thing is, I have shown you the controlling parameters where I mentioned the chemical and physical properties of these precursors. One of the important chemical properties, the pH value. There are studies which shows that while varying the pH values, by keeping all the parameters constant, just vary the pH values and see the morphological changes. In fact, whatever I showed here, one of the picture is taken from that only. That when changing the precursors, the morphology, the shape of the particular particle is changing. Okay, that means you may have neutral or you may not be having neutral. Depends upon your application, what you are looking for. For example, I want my particle size and my particle shape should be this much. Then you have to fix the pH there. If I want to vary it, you can use pH as one controlling parameter. I hope you got the point. Not necessary to make it constant always. It depends on your application and in what way you want to export the material.
Next, any more questions? Please introduce yourself and tell your section also if possible. Students, when you are posing your doubts.
Good evening, sir. I am Dinesh from Automobile Engineering first year. So far, we have learned about nanotechnology and graphics also. So, what are the challenges we are going to face in making them industrially available for the daily life application?
Yeah, that's good thing. So already there are some materials which are already available industrially, especially the nano medicines are available. And some of them are not in the market because of the reproducibility. We're talking about the atomic arrangement, right? though you maintain the conditions same, you may not reproduce the exact whatever you produced earlier. And the one thing where nanotechnology is actually like reproducibility will be there. Understand my point? And the second thing is understanding the properties at the nanoscale level requires a lot of sophisticated tools. Suppose if I want to see the nanoparticle, I cannot use my microscope that I use in my lab. I have to use something called scanning electron microscopy, scanning tunneling microscopy, etc. Isn't it? So the sophisticated tools are available up to some extent, but still, that's the reason I told there is plenty of room at the bottom. It's unexplored because the limitation is the technology development has not happened to reach that point. That is one thing. When the technology develops sophisticated tools to understand it, to see it, to understand the property of the nanomaterial, much more, definitely we can use them industrially. But there are good number of materials are already available in the industry we are using now. For example, we are from automobile, right? Have you seen about nano paints? There are commercial available nano paints, dust-free paints. Okay, waterproof, cloths. These kind of things are not available, and also the strength of the materials is being increased. Lightweight vehicles are coming. Okay, no, where the strength is increased. They're already commercialized. Some, yes, as you said, there are some technical and the fundamental issues may be there. There will be definitely has to be understand the advancing technology. Thank you. Yes.
Yes, any more?
Being the chair of this program, I would like to know, is anybody from outside, like apart from our campus? You can contact me. I can show you our lab where we do. Our students anyway, they want to visit the lab, they can come at any time, no problem. Is anybody from? Can you please contact me after this session? We have some discussion and we'll show you the facilities that are available at our Center for National and Technology, which is there at PG Block, second floor. Okay, you can have some contacts. And the next session is, I think, a networking session where you can have interaction with your friends, the outsiders. If you want to improve your knowledge, if you want to have some clear guidance, if you want to have some expertise, that's it. The IEEE encourages networking. We are here, our IEEE volunteers are here. They will be guiding you. How do we utilize these IEEE sessions for your career growth here? Okay. So as already sir, in the morning session, Subramani sir and Santosh sir told already, right? If you want to meet any scientist or the best engineer in the world, you cannot get even the appointment, right? But if you're IEEE member, you send a mail from your IEEE official mail, they will reply to you. That's the point. All these scientists and engineers in the globe, most of them are IEEE members. That's where you have to enter and explore yourself and search for the opportunities, share your knowledge, and get the knowledge from the people through the networking sessions. Okay? Most of them are first year students. I think you can start registering for IEEE membership and start participating in the activities of the IEEE. We'll be having so many activities in IEEE chapters in our campus. Yeah.
Right. Thank you very much, sir. Thirumal sir. Once again, let us clap for Thirumal sir for his beautiful ceremony. One announcement now, there is a tea break for all, and there is the networking session for outside participants only. For VNRVJIET students and participants, you can make networking at P201, Center for Nanoscience and Technology, after the tea break. The college students can leave after the tea break. You can come to P201 Center for Nanoscience and Technology for networking during any working days. And tomorrow we are going to conduct first session, distinguished lecture 3 by Professor Lan Fu. He is the professor and head of the Department of Electronics and Materials Engineering. He is going to deliver a talk on third and fifth group semiconductor nanowires for electronic applications. We hope all the participants will join for the DL3, Distinguished Lecture 3 tomorrow, sharply at 9:50. Session will be starting by 10 o'clock. Thank you very much for making this function grand success in day 1. Thank you. Session will be started at 10 o'clock, sir. We expect all the participants come here by 9:50.
I think she has sent you his visiting card.
Sorry, we will check it. Sure, summary book or ఎవరన్నా అడుగుతున్నారని